This is tutorial 8, question 1, exercise 7. In this question, we are given a matrix A, 3 by 3, and we are given lambda equals to 4, an eigenvalue of this matrix, and we're asked to find the corresponding eigenvector. So this is how we can proceed. We begin with the equation Ax equals to lambda x, and we are given that lambda equals to 4 is an eigenvalue. Therefore, now we're going to convert the right hand side into matrix notation, because on the right hand side currently it is a scalar multiplying by a vector, or on the left hand side it is a matrix multiplying by a vector. To do that, what we then do is to convert lambda x to be lambda times I x. What is I? I is the 3 by 3 matrix, because we are working with A that is 3 by 3. So I is this. And you realize that lambda times I is equals to simply lambda, lambda, lambda. And lambda I times x will still be equals to lambda x. Now, once we have it in this form, then we can move the right hand side to the left hand side. So we have Ax minus lambda Ix equals to 0. Actually, it doesn't matter whether you choose to move it to the right hand side as well, which is equivalent to 0 is equals to lambda Ix minus Ax. You will achieve the same answer. Now, to solve for the eigenvalue, we need x to be not equals to the 0 vector. Otherwise, this is the trivial solution. We'll continue here. We'll now bring the x out in this way. And for x not being the trivial solution, this equation implies that A minus lambda I must have dependent column, because otherwise it will be, we're trying to find the null space, which is the solution of A minus lambda I x equals to 0. The null space of this equation is the solution that we want, the eigenvector. Now, when we say that A minus lambda I must have dependent column, implying that A minus lambda I is singular. And when we say that a matrix is singular, means it's not invertible, it also implies that the determinant of this matrix is 0. We will use this fact to convert the equation into a polynomial, because what we can see is that in later question, when we convert this into a polynomial, we can find the roots of the equation and hence the eigenvalue. But in this particular question, we are given lambda equals to 4 is an eigenvalue, and we are only asked to find the corresponding eigenvector for lambda equals to 4. So this question is much simpler. We're not solving all the eigenvalues for this characteristic equation. This equation is the characteristic equation over here. This determinant of A minus lambda I will generate the characteristic equation. Alright, let's proceed. We are simply now going to check whether we're given lambda equals to 4, and we want to find A minus 4 I x such that equals to 0. We want to find the set of non-trivial solution. We want to find x that is non-trivial, such that this equation is also true. So what do? We open up, we write the entire A, we multiply 4 by the identity, and we perform this subtraction, and we're trying to still solve for x equals to 0. We got the values, and to find x, we generate the augmented matrix. The right hand side is 0, and we are solving this equation. Perform Gaussian elimination, and then we get this. So the Gaussian elimination is here to trying to make to get the pivots, and we get the pivots. The last equation is consistent. We have one free variable, and that free variable will generate the eigenvector for us. To solve for this, what we'll get is the following. We have minus x1 minus x3 is equals to 0 for the first equation. The second equation is minus x2 minus x3 is equals to 0. This implies on the top is x1 is equals to x3. The second one is x2 is equals to x3. Sorry, it is minus x3 on both sides. Therefore, the vector x is equals to x1, x2, and x3. x3 is the free variable. We can write it this way. The first, by making x3 the free variable, x1 equals to minus x3 means this form. x2 equals to minus x3 means this form. And x3 of course equals to x3, meaning we just set the third element of x to be 1. Therefore, this x3 can be any real number, and this is the eigenvector that we want. In MATLAB, when you generate the eigenvector, we actually normalize it, meaning that we will divide this by its length to get a unit length vector. For sanity check, let's check whether that is our solution. Let's open up the paper here, and let's continue. We now know that x equals to minus 1 minus 1 1 is an eigenvector. For our case, we do not need to normalize it because any scaled version of this vector is an eigenvector. So what we just want to check is that whether the theory is true. That means the matrix A multiplied by this eigenvector is equals to some scalar version, and this scalar version was given to us is 4x. Now let's verify. After brute force calculation, we get this result, and this is the same as equals to 4 multiplied by minus 1 minus 1 1, the original matrix X, showing that it is true. Lambda equals to 4 has this eigenvector. That's the answer to our question. That's it. Thank you.